Hello everyone. I'm making this video to explain about risk analysis under uncertainty, and I'm giving an example of terracing, the impact of terracing on soil loss in this video. As you know, the risk analysis is defined as the assessment of the potential effect of a managerial intervention versus doing nothing. And SWAT has quite a few BMPs that can be used for this purpose. And in the next videos, I will give some examples of the other BMPs that how you can do risk analysis with respect to their effectiveness and also to design the parameters of these BMPs. Now, risk, as you know, is defined as the probability of failure times the cost of failure. And probability of failure is defined as the likelihood of an adverse effect, for example, reaching a contamination threshold or a certain amount of soil loss or having too much runoff, etc. And cost of failure can be expressed in monetary form or in health form or in environmental or uncertainty forms. In this example of terracing, our objective is first to estimate the reduction in soil loss at the outlet of a watershed as a result of terracing, taking model uncertainty into account, and then to calculate the risk of implementing terracing, i.e., to determine whether it's worth it to do terracing or not. The general steps are if you have data available for calibration, then the first thing you do is you calibrate your flow model, and then you set up the model for sediment and you calibrate the sediment. Now, if you don't have data to calibrate the model, it's also possible. You set up your model using the best possible parameters that there are. You can get from the literature or previous work done in the watershed or similar watersheds and so on. Some reasonable range of parameters, and then you use that. Then you set up the model for terracing, and then you run a no observation case for no terracing and for terracing case. I will show you these in the PowerPoint presentation here, and also then in the next video, I will just go to the program and do the steps in the program. So once you do the simulations for terracing and for non-terracing case using the no observation option of SWATCUP, then there are two files. There is a risk exe file and a risk definition file. These two files you copy into the SUFI2 out of the iteration with no terracing and iteration with terracing. And then you execute the risk file and you get a risk output from where you bring that information into Excel and do the rest of the calculation as I will show. So let's go step by step. So if you have data to calibrate your model, then you use that and you calibrate the model and you get your parameter ranges for the calibrated model. If you don't have, then you can use some general parameters that are reasonable for many cases, such as the example that I give here. I also gave this in the previous video. You can use these to get an output from your model. And the reason you can use an uncalibrated model is that we are not looking for absolute values of how much sediment. What we are looking for is the difference between two cases. So if you're looking at the difference between terracing and non-terracing cases, then it really doesn't matter what the parameters are that much. If your parameters are reasonable, you can get a good estimate based on for these two cases. Here are some examples of the parameters that you can use. Now, to set up the SWOT model for flow and to calibrate it, that's the first step. And here I did this. I have an example from a Danube watershed. I calibrated the flow, and here are my calibrated parameters, and this is the result of calibration. Then I set up the model for sediment. That means by adding sediment parameters to the existing calibrated flow parameters, and then I do the calibration for sediment without changing the flow. I have covered this in previous videos. You don't change the calibrated flow parameters anymore, but you do a few iterations for sediment and only change the parameters related to sediment with the new parameters, and then you run a few iterations, and here is my calibrated sediment model. So once I have that, I have done this step here. So the next step is to set up the model for terracing. Now, here you can go to the literature. There is a lot of literature available about the parameters that change when you do terracing. And then we apply those changes in the parameters here. And here are a few references that I have found, and based on these references, I have come up with these values that the change in soil hydraulic conductivity is about 50%. These are delta or percent. The delta is percent change. So the percent change in soil hydraulic conductivity is about 50% when you do terracing. The percent change in soil water storage capacity is about 50%. And the percent change in CN2 is about minus 20%. That means it decreases by 20%. US LEP decreases by 20%, and US LEK also decreases by 20%. So once I have these values, I can change. This is how the values are from. The delta is calculated. Delta is calculated by the terracing minus the non-terracing variable divided by the non-terracing variable. So the terracing variable, therefore, is the non-terracing variable times 1 plus the delta, the change. So these are the changes that we make to these parameters when you do the terracing run. So to implement it in SWATCUP, you apply the changes to par value.text. Now, as you know, in SWATCUP, when you want to do 500 simulations, the program initially generates 500 parameter sets, right? Of these parameter sets, those 5 are the ones that we want to change when we go to terracing case. And this we do in Excel, I will show you. So if you are making relative change, so the new terracing variable or parameter, the new terracing parameter is delta, the delta that I showed before, these values, times 1 plus the relative change that you make to the non-terracing plus the non-terracing parameter value. And here, delta for soil hydraulic conductivity is 0.5, as I showed before, 0.5, 0.2, 0.2, and 0.2 for these other 3 other parameters. So here is an example. This is my parval.txt file. I have done whatever 500 simulations. This is the first 24. And these are the parameters. And I want to make changes to CN2, to soil water capacity and hydraulic conductivity, and then US LEK and US LEP at the end here. And I use this formula to change the values of these parameters. So once I have done that, then I run the no observed iteration for the no terracing case, and then I save that iteration into iter.no-terracing, and then I make the changes for the terracing case, and I make another iteration with no observed option, and I save that iteration to iteration T with terracing. And then, as I said before, you copy these 2 files into these folders, and you run them to get your risk out file. All right. Well, the next step is, how do I make a no observation run? Okay, let's start from parameter information. Now I have calibrated my model, and these are my parameter ranges. Alternatively, you can define parameter ranges based on what you get from the literature for your watershed. You don't necessarily have to calibrate your model. Now, many people ask me after they go through SWATCUP, so where is my model? What is my model? Where is my SWAT model? And many of also still think that ArcSWAT is the SWAT model. But the point is that SWAT model, after you calibrate your model, is parameter information file, the parameters in here, plus the backup folder. The backup folder has your original text in out, plus the parameters in the parim file are your SWAT model that you can use for any future analysis. Now, to make a no observed run in SWATCUP, here is the extract reach no observed definition file. It's straightforward. You just define what program you're using, what output file you're using, the number of variables you want to get, and the variable column number in the SWAT file. And we have sediment out. That's what we are interested. I put an R here to show that it is coming from a reach file. Then the total number of subbasins and the subbasin number for the first variable that you want to extract, the beginning and the end dates, and the time step, which is monthly in our case. The next file you have to fill is the make a no observed run with the SWATCUP is SUFI2 extract batch file. This extract batch file is what you are trying to extract from SWAT files. And here you only need extract reach no observed file. So you only execute this one file. And then finally, you need to complete this SUFI2 post.batch file. And this is the engine of the program that runs executable files. And also what we are interested in right now is the 95 PPU for no observed. That's the only thing that you check. To uncheck those, you have to go to the text view here, and then to remark these other files like this, so that you can only execute this. Now, when you run this, you run it once for the terracing case, as I said, and you run it one, and you save this in the iter no-trace and iter trace, so that you save your files into this iteration. Your iterations, you save them here. And then this is how they look like in our case. And the next thing you have to do, as we mentioned before, is to copy the risk def and the risk exe file into sufi2.out iter no terracing and sufi2.out iter terracing in these two iteration folders. And then the risk definition file has the name of the file that we are interested in to read from. We're going to read from 95 PPU no observed text file. And then we have the number of time steps. And then 10 is the number of probability intervals that I chose. You can choose a different number, but usually 10 should be sufficient. And then you run the risk.exe, and the output of that goes into risk.out file. Now let's look at this. This is the risk.out file for the no-terracing case. So what we have here is soil loss, right? And these are tons. This is the output in the reach file of the SWAT. And this is the probability distribution. Now, I have shown before in an Excel how you make the 95 PPU and all that. So this is how you do the frequency distribution. If you go to that video, you can also see how you can calculate the frequency distribution in Excel, but this is done automatically in the program. So for different soil loss amounts, we have different frequency distribution or probability of soil loss. So if soil loss is very large, of course, the probability is very small. And for small soil losses, the probability is large. And this is with terracing case. With terracing case, the same values are here. So you can see that these are generally smaller than these values with terracing. Now, the next step is to bring those two files in Excel. I will show in the next video. Once you bring them in Excel, we have the soil loss. We have the probability of soil loss here for the no terracing case. The cost of failure is how much does it cost? The loss of 53,769 tons of soil. Because in that soil, the topsoil has a value, the fertilizer in there has a value, the organic matter in this has a value. So you can find from the literature what is the cost or what is the price of losing tons of soil. So here I assume that it's $100 per ton. It's just an assumption. I didn't check with the literature. And if you do, you will find the numbers. So that would be the cost of failure, right? It's this times 100. That would be the cost of failure. And the cost of failure times the probability of failure gives me the risk, right? The risk of failure, and this is the risk. Here is the average, Average here is the expected value, right? We don't call it average because we don't know the distribution, it's normal or not, so it's an expected, the middle is at 50%. So this is the expected risk for the no terracing case. And then you do the same calculation with the terracing, and you see that the risk in this case is 460,656. So what this means is that if doing the terracing, if you do the difference between these two risks, so this would be theoretically the benefit, right? It's the expected saving that you would make if you do terracing. That's the expected saving. If the cost of terracing is less than the expected saving, then you should do the terracing, right? That's the final conclusion, is that if the cost of terracing is less than the expected saving, then it's worthwhile to do the terracing. Now, in the next video, I will go to the program and I do these steps in there so you see how it is done. Thank you for your attention.